All right, welcome back. Um, from our last discussion, we've concluded chapter 9, and now we move on to chapter 10 in our textbook, and we're going to talk about testing variables that are categorical. Okay, so we're going to see some familiar contingency tables that we saw before in the beginning of class, but now we're going to formally determine whether variables are dependent or associated somehow or not. So last time, we're looking at political party and opinion on accepting Syrian refugees, and what we found is that people from the Democratic Party were much more likely to say yes to Syrian refugees versus people from the Republican Party. There's definitely big differences there. So what we could have concluded was that, definitely your opinion on whether to accept Syrian refugees or not, it definitely is associated with your party. So no cause and effect here, but we're just saying we observe association. So as far as what the data could look like, one way we could see when categorical variables are analyzed, they are often displayed as a contingency table or a two-way table. Okay, a summary table that displays frequencies or outcomes. So, and we've seen this before, right? We've seen these contingency tables in the very beginning. It's just the way we count categorical variables, right? So this 166, it means there was 166 Thanksgiving dinners where there was no pumpkin pie and no pecan pie. Okay, and then here we see there's 265 Thanksgiving dinners where they had both pumpkin pie and pecan pie. So we've gone through these numbers here. We've gone through these numbers and we counted them. We see the contingency table when we want to test whether two variables are independent or not. So here our variable is pumpkin pie, yes or no, and the other variable is pumpkin pie, yes or no. So what we want to know is whether these two variables are independent. So maybe, given that I'm in a house that doesn't have pecan pie, how likely is it that they also don't have pumpkin pie? Things like that, right? I mean, or are these outcomes completely independent? Meaning when I walk into a house and there's no pumpkin pie, well, it's still random chance or same chance of me getting the pecan pie, right? So, of course, you may be familiar with this one. Okay, so when we get into so usually what we do is we compare what we observe to what we expect. Okay, so how do we get these expected counts? All right, so here we say are the numbers of observations we would see in each cell of the summary table if the null hypothesis were true. So for this example here, we're just saying, okay, I'm going to play this roulette wheel, and this should be familiar from the exam that we have, okay, our last exam. Okay, but here I'm just saying, hey, there's 18 red, 18 black, 2 green, each outcome's equally likely. I'm going to bet on red 3 times and record the number of wins. So, I'm gonna do this bet of 3 over and over and over and over again. And what are my expected outcomes here? So if the wheel's balanced and the way it should be, then the probability of 0 wins is about 14.6%. Probability of 1 win is 39.3%. Probability of 2 wins out of 3 is 35.5%. Probability of 3 wins out of 3 is 10.6%. Okay, so you had to tackle this probability on the exam, so you're pretty much familiar with it. But so these are my chances of winning this many times out of 3 plays. But suppose that I'm gonna play 50 times. Okay, I'm gonna play this game 50 times. How much would I expect to win? Right? How many times would I expect to win 0 times, or expect to win 1 times, or expect to win 2 times? Right? So pretty much what we do is, this is saying, 14.6% chance of 0 wins, right? So if I play 50 times, 14.6% of those 50 should be the expected number of times that I win 0 times out of 3 plays. Okay, so here this is 7.3, right? Expected 7.3. Right, and of course here, I'm gonna play the game 50 times. How many times would I expect to win? one win out of the 3. Okay. Okay. So what do I get here as well? I mean, well, this is just well, the probability of winning once is 39.3%. So if I just took 39.3% of 50, that would give me the number of times I expect to win 1. Okay, now and here I get 19.65. I do the same for 2, 17.75, same for 3, 5.3. So these are the expected outcomes I should see, given that, you know, the wheel is working the way it should be, and my modeling, how I model it, is correct. Okay, now what I do, so these are like theoretical. Okay, these are what, you know, the null hypothesis, right? Under the null hypothesis, assuming I got it right, this is what I expect to see. Then I go play the game. Okay, actually go play the game. And when I play the game 50 times, 10 times I have 0 wins, so, you know, I lost a little more than I expected. 14 times I get 1 win, which is a little less than what I expected. 17 times I won 2 out of 3, so right around what I expect. And then 3 times I won 3 out of 3, right? So a little bit more than I expect. Okay, so with these tests, what we do is we say, okay, well, okay, there's obviously differences here between expected and observed. Okay, we get, you know, 2.3 difference, 5.65 difference, 0.75 difference, 3.7 difference, or something like that. Okay, so there's obviously differences here, but is this observed data far enough from what we expect such that we would conclude that, hey, you know what, this model's wrong. Okay, this model's wrong. Okay, so that's what we'll get into soon. Now, we'll also deal with expected counts for independence. So when we're dealing with these tests, either we're doing a goodness of fit or we're doing independence. So goodness of fit is just say, look, here's the model, right? Here's what I expect to happen, and here's the outcomes I expect to be within each outcome, and then we compare it to the observed. Whereas independence, we're just saying, hey, here are 2 variables, pecan pie, pumpkin pie. Are these independent or not? Right? So in finding the expected counts here, well, how do we do that? Well, under the null hypothesis, we assume that the variables are independent, right? Versus the alternative that not independent. Okay, so notice one thing here, the hypotheses, we don't have the Greek letters anymore, right? We don't have mu's, we don't have p's, or difference in mu's and difference in p's, right? It's just words, right? So my null hypothesis in this case would be, oh, it's a fair, perfectly balanced wheel, right? That would be it for me. And here, it's just variables are independent, right? So remember, if events A and B are independent, then probability of A and B is equal to the probability of A times probability of B. Okay, so if I wanted to find the expected counts within a cell, okay, I would do my total number of observations times the probability of A and probability of B. Okay, of course, it's really the probability of A and B, the percentage, right? We want to talk about percentage, right? We're just saying, hey, if the null hypothesis were true, the percentage of outcomes that are both in A and B, well, that would just be equal to the percentage of A times the percentage of B, okay, if independent, okay? So that's what we're saying here. If we want to find our counts, it's just n times that there, okay? Okay, before, with the roulette wheel, while we knew the probability of red was 47.4%, the probability of not red was 56.4%, and so from there we're able to calculate all the probabilities and things like that. Okay, so let's go back to this example. Okay, we say, are the dishes mashed potatoes and gravy independent? Okay, so on the columns I have gravy, okay, and on the rows I have mashed potatoes. Okay, so here this 154 means 154 dinners did not have mashed potatoes. 817 here means 817 dinners had mashed potatoes. This 81 here means 81 dinners did not have gravy, and this 890 here means 890 dinners did have gravy. Okay, so we're going to need these totals here to calculate this probability of A times probability of B. Okay, so it says if independent, then the probability of no potatoes and yes gravy equals probability of no potatoes times probability of yes gravy. Okay, so we're just using that independence here. but we have to estimate the probability of no potatoes and the probability of yes gravy. Okay, so we're going to use empirical probabilities. Okay, finding percentages that we did before. All right, so probability of no potatoes means it's 154 over the total 971. Probability of yes gravy is the 890 yes gravy over 971. So we get our two empirical probabilities here. Now, if we want to find the expected number of dinners we would expect to see there, okay, in this count, well, then we just take our total sample size, 971, and multiply it by this percentage here, by this probability. So if we did 971 times the probability of no potatoes times the probability of yes gravy, we would get 141.15. Right? So obviously there's a slight difference between here and there. Okay. So the nice thing about StatCrunch is that, of course, we have to do this for every cell. We're not done yet. We're not done yet. We would have to do it for every cell. So there's 1, 2, 3, 4 cells. So we have to repeat this calculation for all 4. And I encourage you to do that to make sure you understand what we're seeing in StatCrunch. Okay, so that's what we get here. Okay, so in StatCrunch, not only can you have it give you the contingency table, but you can also have it give you the expected counts here as well. And here's 141.15. Okay, because in the previous example, we found the expected counts for every possibility, so we do the same thing here. Okay, so here, that's expected count, expected count, expected count. And if you look at all these, I mean, there is a clear difference between the expected counts and the observed counts. Okay, so expected counts usually give away that they're decimal, but they're in the parentheses here, right? So what these represent, these numbers here in parentheses, these are expected number of outcomes we should see, given that the variables mashed potatoes and gravy are independent of each other. Okay, so what it's saying is that, you know, given that there's mashed potatoes at dinner, it doesn't change the probability of there being gravy. Okay, or given the chance that there's gravy served at dinner, that doesn't change the probability of whether or not mashed potatoes are sold. Okay, that's assuming independence. Right, so if I go here, let me just show you real quick, it's StatCrunch. So let's see, mashed potatoes and gravy. So let me go to my featured data sets here. Let me go to Thanksgiving. Okay, so I'm gonna do stat, and then I'm gonna do tables, and then I'm gonna do contingency table with data. Okay, so I'm gonna plug in with data here. So my row variable was mashed potatoes. Okay, and my column variable was gravy. Okay, gravy right there. Okay, and so here you can ask it to do a whole bunch of stuff for you, right? So here you can say, hey, give me the chi-square test for independence, because that's what we're going to do later on. And then here you can ask it to give you the expected count. Okay, the expected count. Okay, so what it's going to do, with that expected count, is the expected count assuming that variables are independent. Right, so it's going to do those calculations that I was doing by hand previously. Okay, so if we can compute it, boom, there it is. Okay, so here we get our table, okay, with the counts and the expected counts here. So very, very slick, and it gives us, and right away, you know, the way they set it up is that we can easily compare, right, the observed count with the expected counts, right? And we see, like, because they're all pretty, I mean, there's a big difference between all of them. Right, so maybe that's assuming that, you know, if there's a big difference, it's kind of assuming that these are not independent, meaning that, you know, if mashed potatoes are served, the probability of gravy has increased. Right, that's pretty much what we're saying when they're dependent. Right, or it could decrease. It could decrease. Of course, it takes a little bit more work to figure out, you know, what that is. But anyways, there's some dependence there. Okay. So very nifty in StatCrunch here, and that's what we get there. Okay, but so I mean, here we observe. Okay, so here under the null hypothesis, we observe our data. Okay, under the null hypothesis, we find the expected counts, and now what we're unofficially doing is seeing if there's a big difference. Right, there's a big difference. So really, how do we combine this information together to make a decision? Meaning, what's our test statistic here? Right, so our test statistic here is called the chi-square statistic. Okay, it's not the chi squared, it's not the chi square, it's the chi-square statistic. Okay, so the chi-square statistic is a statistic that measures the amount that our expected counts differ from our observed amounts. Okay, so this is what we call the chi-square test statistic. And pretty much what it does for each cell, it'll take the difference between the observed and expected, and then it'll square it. And then what we do is we kind of standardize it by the expected value. Okay, but we can't just take the difference because it is an average. So the sum could be 0, and that's not what we want, right? So we want to, because we're actually measuring all the differences. So that's why we square the difference. Okay, we square the difference here. And then here we're kind of standardizing the square difference by dividing by the expected count here. Okay, but here you can tell, because this is expected number of outcomes, so this is always positive, the numerator is always positive, so this chi-square test statistic is always going to be greater than 0, right? So if it's a lot larger than 0, we're going to reject the null hypothesis. If it's very close to 0, then we're going to fail to reject the null hypothesis. Okay, but O here represents observed count in each cell, E is the expected count in each cell, and the sigma is just saying, hey, for each cell, do this, and then add them all up in the end. Okay, and we will reject the null hypothesis for large values. Okay, so if we look here, if I were to do this by hand here, okay, so actually in the table I showed you earlier, this right here, the statistic, the value 33.26, that is the chi-square test statistic. So that is larger than 0 for sure. Okay, and here it tells you the degrees of freedom. Okay, but so really quick as far as here, so here's just the hand calculations. So for each cell we do observed minus expected squared divided by expected, and then we do it again, observed minus expected squared divided by expected. Okay, next one, observed minus expected squared divided by expected, and then one more, observed minus expected squared divided by expected, and then we add them all up. So that's what each of these are doing. That's what each of these are doing. They're adding each one up. Okay, then if you do that, you get 33.26. Okay, so the data conform to the null hypothesis. So we're saying here is that if the data conform to the null hypothesis, meaning that these outcomes are independent, then the value of the chi-square statistic will be small. Okay, and this is true for both goodness of fit and independence types of chi-square. Okay, for this reason, large values of the chi-square statistic makes us suspicious of the null hypothesis. All right, so in this case, we're going to become very suspicious of the null hypothesis. Okay, so here, so really the degrees of freedom here, the one thing that changes, we'll visit it right now. Okay, so anyways, as far as finding the p-value, so pretty much we say, okay, so as far as p-value goes, we say what's the probability of observing our data 33.26 and more extreme values, assuming that the null hypothesis is true, which is in this case assuming that the variables are independent, right? If this p-value is very small, meaning we have a surprise, we're going to reject the null hypothesis. Otherwise, we're going to fail to reject. So over here, it's already telling us that this p-value is very, very, very small, meaning that you're going to reject the null hypothesis and conclude that these variables are indeed dependent. Okay, meaning that given that gravy served at a dinner, it's definitely going to change the probability of there being mashed potatoes or not. Okay, but really quickly, the chi-square distribution is another one of those famous distributions that we use. That's another famous kind of like sampling distribution. Okay, for sample standard deviation. But here is just saying that the chi-square distribution provides a good approximation to the sampling distribution of the chi-square test statistic, only if the sample size is large. So once again, this is another approximation, right? So for many applications, the sample size is large enough if each expected count is 5 or higher, right? So sometimes your observed counts may be less than 5, but what we need to check are the expected counts that are 5 or higher within each cell. Okay, so I mean each number we get has to be 5 or more. So just one thing to know about this chi-square distribution is that it's definitely unimodal, it is not symmetric, and it's skewed to the right. And if you look at the values of the chi-square or this x-square test statistic, it's only non-negative. Okay, you won't see any negative values down here. Okay, one thing to know is that as degrees of freedom increase, right, it's kind of shifting over to the right a little bit, kind of looking a little less skewed. Okay, but nonetheless, this is kind of a skewed distribution. right? And one thing to note as far as like, in most cases, the degrees of freedom, if we're dealing with independence, okay, right? If we're dealing with independence, okay, the degrees of freedom, okay, the degrees of freedom, they're gonna be equal to your number of rows minus 1 times the number of columns minus 1. Okay, so that's what we're saying here, is that the degrees of freedom here are number of rows minus 1 times the number of columns minus 1. And if you think about degrees of freedom here, right, we're saying, if I go back to this original table here, okay, we're saying, so suppose I know these numbers here, I know everything here. Well, how many of these 4 numbers do I need to know in order to know all of them? Okay, so let's say I knew 31. Well, then 154 minus 31 gives me 123. 81 minus 31 gives me 50. And if I add all these up, subtract from this, I get 761. So given this information here, all I need to know is this. All I need is one piece of information to know everything, right? So that's why my degrees of freedom here, my degrees of freedom in this example are 1, because I only need to know one piece of information to know all the cells, right? I only need to know one cell in order to know all the cells. So degrees of freedom here, they're more related to the number of cells, because there's 4 cells here, and not the sample size. Okay, so previously we saw degrees of freedom, it was like 9, you think 971 minus 1, right? Your sample size minus 1. And that's not the case here. When we're talking about these goodness of fit or chi-square statistics, we're talking about the number of cells here. Okay, so just saying, I just need to know the outcome of one cell in order to know the rest. Okay, but in general here, the degrees of freedom are number of rows minus 1 times number of columns minus 1, right? So in this case, which we just saw, we got 2 minus 1 times 2 minus 1, and that gives us 1 times 1, which is just 1, our degrees of freedom. Okay, if it were a 3 by 3 table, then we would do 3 minus 1 times 3 minus 1, we have 4 degrees of freedom. Okay, that's just a little gist on how they find the degrees of freedom there. Now I can use my chi-square calculator to find my p-value as well. So here I just put in my degrees of freedom, which is 1, and here I put in the probability of observing 33 or larger values. So the p-value, for these hypotheses tests, for the contingency table, the direction of the p-value or goodness of fit, there's no different alternative. There's no one-tail, two-tail test in dealing with, in chapter 10, and dealing with the categorical. It's either independent or not, or it follows its distribution or not. And we're always going to reject the null if our chi-square test statistic is large. Okay, is large. So in finding the p-value, it's always going to be probability of greater than or equal to what we observe here. Okay. So in dealing with categorical variables, goodness of fit, independence test, there's no such thing as one tail or two tail test anymore. Okay, we're always going to reject if this chi-square statistic is large. Okay, so it's always going to be greater than or equal to 33. And just how I use this calculator here, I'll just show you very quickly. Okay, I do stat calculators, and there's the t, right? But here I want the chi-square. So chi-square, I would just go in here and plug in 1 degree of freedom, and then of course I have to switch this right away to greater than or equal to, and then I would put in 33 and then compute. Okay, so this e to the negative 9 here, it just means go 9 decimals to the left. So you go, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you get a number that's very, 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 very close to 0. Okay, very close to 0. Okay, so what this result is saying here is that, well, the probability of observing, assuming that mashed potatoes and gravy, these variables are independent on Thanksgiving dinner, okay, the probability of observing our test statistic of 33 and larger values is pretty much impossible. Okay, it's a very, very, very small probability. Okay, so a surprise occurred. So in this case, we would conclude that yes, We would reject the null hypothesis and say these variables are in fact not independent, and conclude that they are dependent somehow. Okay, now how are they dependent? Well, we have to dig in here and find some conditional probabilities to kind of uncover what this dependence looks like. But I would assume maybe if mashed potatoes are served, you're more likely to get gravy, okay, than just by getting gravy by itself. Okay, all right. But next time we're going to do an official hypothesis test for the goodness of fit.